Welcome to the deep dive. Our mission today is not just about understanding a piece of technology. It's about studying what was really an intellectual earthquake.
Hmm.
We're looking at a single pivotal academic paper from 2017 that didn't just improve AI. It basically threw away the rule book. It got rid of the complex recurrent neural networks that everyone thought were essential for language.
That's absolutely right. We're diving into Attention is All You Need. It was presented at NIPS 2017 by a team from Google with authors like Ashish Vaswani, Noam Shazir. This paper introduced the transformer architecture,
Right.
and that is the direct ancestor of, well, pretty much every major large language model you hear about today.
The genius is right there in the title, isn't it? It's such a radical statement. Before 2017, if you wanted to translate a sentence, you relied on these sequential models.
RNNs, LSPMs, GRUs, all of them.
Exactly, and they had to keep this detailed memory state as they went word by word, which was slow. The transformer proposed just dispensing with recurrence entirely.
All of it, using solely attention mechanisms.
So our goal for you, listening, is to really get how this revolutionary shift was possible. We want to unpack why relying just on attention resulted in, better quality, radical parallelization, and just way lower training costs.
And this wasn't just a small step up. It was a fundamental change in how we process sequence data.
So let's set the stakes. What was the actual real-world consequence of this?
Speed and performance
Mm.
at the same time. The transformer just shattered the records of machine translation. It surpassed these really complex models, even ensembles of models.
Wow.
And the crucial part is that the biggest, most powerful versions trained in a matter of days. The base model trained in just 12 hours.
Not weeks or months like before.
No, not at all.
Yeah.
Basically altered the entire economics of AI research overnight.
Okay, so to really get the breakthrough, we have to understand what they were replacing. You mentioned RNNs were state-of-the-art for sequence modeling.
For about 2 decades, yeah. They're designed to process data one token or one word at a time, in sequence.
Which leads you straight into the main problem, inherent sequential computation.
It's exactly.
If I have a 500-word paragraph, the model literally can't look at word 500 until it's processed words 1 through 499.
Right, because the hidden state for time stack 2 depends on the hidden state from T-1.
It's literal
Chain reaction.
It's a literal chain reaction, and that's the bottleneck.
That's the bottleneck that kills efficiency. It makes it impossible to parallelize within a training example.
Yeah.
You can't just do all 500 words at once. You have to wait. And for long sequences, that constraint is crippling.
Now, attention mechanisms weren't totally new, right? They were already part of these models.
They were, yeah, but they were always used with a recurrent network. Attention was sort of a passenger, not the driver.
Okay.
People had tried to solve the sequential problem before, with convolutional models and things like ByteNet.
Mm-hmm.
But the transformer was aiming for something unprecedented.
Yeah.
They wanted to reduce the path length between any 2 words in a sequence to a constant number of operations.
To 01.
To 01.
And that 01 is really the punchline. The old RNN system is like that game of telephone, right? The message goes step by step, and it gets distorted by the time it reaches the end.
That's a great analogy. And the transformer, by getting to 01 complexity, is like instant messaging. Every word is directly connected to every other word all at once.
And that's what unlocks that massive parallel processing.
That's big.
Okay, so let's unpack the architecture. It did keep one familiar piece, the encoder-decoder structure.
Right, that was pretty standard for tasks like translation. The encoder is a stack of layers. The paper used 6 identical layers, and each layer has 2 parts, a multi-head self-attention mechanism, and then a simple feed-forward network.
And the decoder is similar?
Very similar. Also a stack of 6 identical layers. It has the same 2 parts as the encoder, but it adds a crucial third one in between them, the encoder-decoder attention.
Ah, and that's how the decoder can look at what the encoder did.
Precisely. It lets the decoder query the fully processed output from the encoder. And importantly, everything is wrapped in residual connections and layer normalization to help it train properly.
So this gets us to the central problem, the million-dollar question. If you throw out the sequential processing of an RNN, how does the model know that word A came before word B?
It doesn't, not on its own. The self-attention mechanism just sees a bag of words. It has no concept of order.
So the sentence is just dumped in all at once.
Exactly. So you have to manually inject that information back in. They called it positional encoding.
It's like stamping a little sequence ID, a timestamp onto each word.
That's a perfect way to put it. They add these encodings to the input embeddings right at the very bottom of the stack. And what's really interesting is how they did it. They didn't learn them. They used fixed mathematical functions.
Sines and cosines, right. Why do that instead of just letting the model learn the positions itself?
Well, they tried learned embeddings too, and said the performance was pretty much the same. But they went with the sine and cosine functions because they hypothesized it might help the model generalize
To what?
to sequence lengths that are longer than anything it saw during training. It was a strategic bet on scalability.
Okay, that makes sense. Let's move to the real heart of the paper then, the attention mechanism itself.
Right.
What were the big innovations there?
There were two main ones. The first is what they call scaled dot product attention. The idea is simple. You compute the dot product between your query and all the keys, you apply a scaling factor, and then you put it through a softmax to get your final weights.
And you mentioned the scaling factor, the 1 over the square root of dk.
Yeah.
Why is that little division so important?
It's all about numerical stability. If the dimension of your keys, dk, is big, and here it's pretty big, the dot products can grow massive.
Okay.
And when you feed huge numbers into a softmax function, the output becomes really peaked. It pushes the function into areas where the gradient is almost zero.
And if the gradient is 0,
The model stops learning. It just flatlines. So that little scaling factor keeps the numbers in a healthy range and lets the network train efficiently. It's a subtle but absolutely critical tweak.
that's fascinating, a tiny math fix that enables the whole architecture. Okay, what was the second innovation?
Multi-head attention. This one is a bit more intuitive.
Okay.
Instead of having one big attention calculation, they run the attention function multiple times in parallel. The base model used 8 parallel heads. Each one projects the query's keys and values into a lower dimensional space and does its own attention calculation.
So it's like having 8 experts look at the sentence at the same time instead of just one.
Exactly. And then you just concatenate their outputs and project it back to the original size.
So why is that better? Why are 8 smaller heads better than one big one?
Because it allows the model to jointly attend to information from different representation subspaces. Think of it like this. One head might learn to track syntactic relationships, like subject-verb agreement. Another head might focus on semantic meaning, like figuring out what a pronoun refers to. If you only had a single head, averaging all those different goals would just wash everything out. It couldn't focus. Multi-head gives it 8 different lenses to view the input.
That really clarifies it. So let's quickly go over the 3 ways they actually use this multi-head attention in the model.
Sure. First, you have the encoder-decoder attention. This is in the decoder. The queries come from the decoder itself, but the keys and values come from the output of the encoder. It's how the decoder looks at the source sentence.
Standard cross-attention. Makes sense. Second.
The encoder self-attention. Here, the query's keys and values all come from the output of the previous layer in the encoder. So every word is looking at every other word in the previous layer's representation.
That's where the O1 path length really happens.
That's it. And finally, the third one is the masked decoder self-attention.
The masking sounds important.
It's critical for generation. Because the model produces the output one word at a time, you have to prevent it from cheating and looking ahead.
Right. It can't know the future words it's about to generate.
Exactly. So the masking just blocks those connections. Inside the attention calculation, you just set the scores for all future positions to negative infinity, which makes them 0 after the softmax. It preserves that autoregressive property.
Okay, that covers the mechanics. Let's get to the results, because this is where the theory meets the road. And the performance wasn't just a small improvement, it was a massive upgrade.
It was staggering, yeah. On the WMT 2014 translation tasks, the results just reset the whole field. For English to German, which is a very tough task, the big transformer model hit a BLEU score of 28.4.
And for anyone listening, a 2-point jump in BLEU score isn't just good,
It's an earthquake. It blew past the previous best results, even ones that used huge ensembles of models.
So it proved that efficiency didn't come at the cost of quality.
Not at all. For English to French, it hit a new single model state-of-the-art of 41.8 BLEU, and the training time really drives the point home. The big model got these scores after just 3.5 days on 8 GPUs.
Which was what, a fraction of the previous cost?
A tiny fraction. This is what made massive scale truly feasible.
And this all comes back to that computer science advantage, the parallelization. When you look at the metrics side by side, it's just so clear.
It is. The self-attention layer has a minimum number of sequential operations of O1, one step. A recurrent layer requires ON steps, where n is the length of the sequence. It's a night and day difference.
And for learning complex relationships, the key metric is maximum path length.
Right. And for self-attention, that path length is O1. Word 1 and word 500 are connected in a single step. For an RNN, that path is ON. A signal has to travel through 498 intermediate steps, getting weaker and more distorted the whole way. Long-range dependencies were just exponentially harder to learn.
So beyond the performance, there was also this unexpected benefit, interpretability.
Yeah, that was a really nice side effect. Because attention gives you these explicit weights, you can actually look inside the model and see what it's focusing on. You can visualize the attention distributions.
And they found the different heads were actually specializing, learning to do different jobs.
They absolutely were. It wasn't just a jumble of weights. They showed examples where one head was clearly learning about syntax, another was tracking dependencies across long distances.
And they had that great example of anaphor resolution, right?
They did. For a sentence about a law, when the model was processing the word "it's," one attention head would just light up, focusing almost all of its attention directly on the word law from earlier in the sentence.
So it was explicitly learning that grammatical relationship.
Exactly, which really validated the whole multi-head design. And this wasn't just a one-trick pony for translation. They applied it to English constituency parsing and got great results there too, even with less data. It was just a fundamentally better architecture.
So as we wrap up this deep dive, the key takeaway feels really clear. The transformer proved that attention alone, without any recurrence or convolution, is enough to get state-of-the-art results.
And at the same time, it unlocked this incredible parallelization. The big idea, I think, is that knowledge isn't about sequence. It's about connections. Just letting every part of the input connect directly to every other part, that was the breakthrough.
Which brings us to a final thought for you to chew on. The authors themselves brought this up in their conclusion. The core advantage here is reducing the path length to O1 for any sequential data. So if it worked this well for text, what happens when you apply this attention-only architecture to other things? To images, to audio, to video? If frame 500 of a video can connect instantly to frame 1, what new kinds of complex dependencies might these models suddenly be able to learn?